Okay, so using the Crank-Nicholson method, we start off by saying that the change in temperature over the change in time is equal to alpha times the second derivative of temperature over 2x squared. Okay, so we can rewrite this side as tj to the n plus 1 minus tj to the n over the change in time. And then this side becomes alpha over the change in x squared all times tj plus 1 to the n minus 2 tj to the n plus tj minus 1 to the n all over tj plus 1 to the n plus 1 minus 2j n plus, to the n plus 1 plus tj minus 1 to the n plus 1. Okay, now we can simplify this a little bit by saying that r is equal to the change in time times alpha over, there should be a 2 here because we're taking the average, so it's over 2. 2 times the change in x squared. So plugging this in and rearranging a little bit, we can get tj to the n plus 1 minus tj to the n equals r. So we're replacing that with r. And then all of this comes down. So tj plus 1 to the n minus 2tj to the n plus tj minus 1 to the n. tj plus 1 n plus 1 minus 2tj to the n plus 1 plus tj minus 1 n plus 1. Okay, so from this point we can further rearrange it, and so we can end up getting negative r t to the j minus 1 to the n plus 1 plus 1 plus 2r times tj to the n plus 1 minus rtj plus 1 to the n plus 1 equals rtj minus 1 to the n plus 1 minus 2r times tj to the n plus rtj plus 1 to the n. Okay, so this side is our unknowns, and we know this side because this is the initial or 0. So breaking this down into matrices, we get, so this is starting from j equals 0, j equals 1, all the way down to j equals 49. So this would be the coefficients. Noticing some of the trends, so it starts off, the first one's the j equals 0 starts off at negative r, and then we get 1 plus 2r, then we get negative r, and then 0 after that. Now, going down, we know that the negative r's, the trend goes diagonally down. And then this eventually ends up to be 1 plus r down here at j equals 49. And then the second matrices, this just is the tj to the n plus 1 column. So this would be t0 n plus 1, t1 n plus 1, all the way down to t to the 49 n plus 1. And then it'll equal j equals 0, j equals 1, all the way down to j equals 49. And then we get rt, and then it's all the way, this is the left boundary, so t left to the n plus 1 minus 2r tj to the n plus t j plus 1 to the n plus rt left boundary to the n. And then the next one, when j equals 1, we get rt j minus 1 to the n plus 1 minus 2r tj to the n plus rtj plus 1 to the n. Now, this one happens to be the same all the way down until you get to j equals 49. Once you get to j equals 49, you end up getting rtj minus 1 n plus 1 minus 2r tj to the n plus rtj plus 1 to the n plus rtj plus 1 to the n. So this can be simplified a little bit by factoring out and everything. So we end up getting, for j equals 49, we end up getting rtj minus 1 to the n plus tj to the n. And then for t, oh, it should be a t. And then for tj to the n, it equals tj plus 1 to the n. Okay, so the first thing we're going to do is we're going to import all of our functions. So we're going to import numpy as np from plotly.subplot. This is for plotting. Subplotting. Import make underscore subplot. Import plotly.io as PIO. POI is one. From cp.algebra. Import solve underscore banded from the C. Alright, good. Okay, so now we're going to start setting everything up. So the length of our bar, the length is equal to 50. We'll set the time. We want to know intervals up to 3,600 seconds. The initial temperature, for right now, we'll do equals np dot full, and then length, and then 20. Then we'll go t underscore in. The first is 50 because that is our first initial temperature. 50 at 0 seconds. And then our alpha will be 1. Our change in position will be 1. dt will be 1. X will be np dot arrange length times dx, which is just 1. And then we'll set our R equal to alpha times dt divided by 2 times dx to the second power. Alright, good. Okay, so now we're going to start setting up our matrices. So our first matrices we'll set it as coefficients. And it'll be NP, we'll set it up zeros, the length minus 1, and then we'll do the co-underscore-efficients, semicolon, equals negative R, co-underscore-efficients, equals 1 to 48. That will be equal to 1 plus 2 times R. And again, we're just getting this from the Crank-Nicholson equation that we solved for in the first part. And co-underscore-efficients. Then we'll go from 148 equal to 1 plus R. Then co-underscore-efficients. We'll go from 2 equals negative R. Run this. Okay. Let's add another code bar. Okay. Now that we have that set up, we're going to set up our second matrices. So we'll do matrix underscore 2 equals np dot zeros from length minus 1. And then we'll start making the plot. So figure equals make underscore subplots, and then we'll have the row equal to 1, and then columns also equal to 1. And then figure dot add underscore scatter. We'll set x equal to x. Sorry about the noise if you can hear that, my house phone. We'll have y equal to the initial temperatures, and then the name will be initial. Rows. So I was missing the S, that's why. Okay, perfect. So now we have that. So now, let me get rid of that for a second. Now we're going to start we'll start adding the other lines. So for I in range from 1 to time plus 1, we want to, well, there we go. For matrix underscore 2, for 0, the first slot want to set that equal to equals r times t underscore n to 0 plus 1 minus 2 times r times t underscore n, first position, well, I guess second position, plus r times t underscore n in the second position. Okay, and then we want to do n at 0 equals this plus r times t underscore n at the 0 position. We'll do the matrix 2 again, but instead from the 0, we'll do 1 to 48. We'll set that equal to r times t underscore n from 1 to 48 plus 1 minus 2 times r times t underscore n from 2 to 49 plus r times t underscore n, and then 3 semicolon v. Okay, so now we want to do at 48. So 48 will equal r times t underscore n at 47 plus 1 minus r times t, that's y, t underscore n at 48. And then our t underscore n from 1 to 50 will be equal to, this is where our solve underscore banded function comes in. Banded, we'll do 1, 1, and then we'll use co underscore efficient, and then matrix underscore 2. And then for sake of plotting it, we'll do every 300 seconds. So if the remainder of I, by dividing it by 300, does not, or if it does equal 0, then we will add it to the graph. So underscore scatter, x equals x, y equals t underscore n. Mode will be lines, and then the name will be just the time. And then we want to show it. All right, run. This should have that there. That didn't turn out the way I wanted it to. We'll try this. And there you have it. Initial 300 seconds, 600 seconds, 900. It goes all the way down to 3600 seconds.